Hello, everyone. Welcome to ConnectCon, presented by FTC Team 9794, Wizards.exe. Join us this week on our magical journey each day from 10 to 11 a.m. and 2 to 3 p.m. Eastern Time, where you can hear from STEM professionals from Google, APL, iRobot, and more. My name is Ronak Banerjee, and I'll be your host for this session. Please use the chat for any questions related to the presentation, and we'll address them at the end. Today, we're honored to have Mr. Paul Biermann speaking about the JHU APL Advanced Mechanical Fabrication Lab. Mr. Biermann is an APL master inventor and holds many US patents. He has an extensive knowledge in material selection and fabrication of structures and components. He will be giving us a virtual tour of the facilities where he works in, discuss the different fabrication methods available, and walk through how a part goes from design to production. Many of my teammates here are engineers, so I'm sure they'll be interested, and I hope you all are too. Thank you, Mr. Biermann, for taking the time to present at ConnectCon. Without further ado, let's begin.
Good afternoon. As it said, my name is Paul Biermann. I'm a materials and process engineer, which means when someone comes up with a design, something they want to build, they have to figure out what materials to build it out of. And that's where someone like me comes in the story. You can look around you at just about anything in the room that you see, and someone had to figure out what material it was made out of and how to process it. That's why I have a job. So here at APL, we do all kinds of research for our customers, the US government primarily. And as part of that, we tend to build a lot of prototypes or one-off designs to try out an idea, to test theories, and also to work up a new product that potentially our customer might want to have someone produce. We're not in the business of doing mass production. So I'm going to flip over to some view graphs. I'll give you a little introduction to APL. And what we're going to do is watch a series of video clips that you can find out on APL's YouTube's website. We put a lot of information out there that people can look at, but I picked some select ones that are going to help describe the areas that I do work in and the areas that we interface with, and then some examples of some of the things we built over the years. So let's see if I can make the share screen work here. Okay, and okay. And there we go. Can everybody see that? So we're going to talk about fabrication technologies at the Johns Hopkins University Applied Physics Lab. There's my email if people want to contact me with questions at any point. I will try and respond, but some days the email box gets pretty full. So, Johns Hopkins APL. Basically, we solve complex research, engineering, and analytical problems that present critical challenges to our nation. APL, the nation's largest university-affiliated research center, provides U.S. government agencies with deep expertise in specialized fields to support national priorities and technology development programs. We also serve as an independent, trusted technical agent to the government, providing continuity for highly complex, multi-generational technology development systems. Our purpose is to make critical contributions to critical challenges. At APL, we feel it is our responsibility to try and solve these national challenges with the full measure of our dedication and expertise. So what I'm going to show you first, this video clip takes you through not just the additive manufacturing, but actually our complete mechanical manufacturing area. The person narrating the video is actually my office mate. His specialty area happens to be metal additive manufacturing and welding. So without further ado, let's kick this off.
Welcome to Building 15. This is a fabrication hub for APL where we do mechanical fabrication, additive manufacturing, which is better known as 3D printing, and engineering materials. Let me show you around. This is mechanical fabrication. This is where we do things like machining, welding, and sheet metal fabrication. This 5-axis vertical turning machine is one of the many ways that APL is investing in the future of manufacturing. This machine allows us to address next generation sponsors' needs like hypersonics in space.
Currently, I am working on a fixture for the Space Department. It is a gimbal housing. This machine gives us the capability to run all 4 operations in one setup, which saves a lot of time.
Thanks, Paul. Mechanical fabrication isn't just machining. It's also things like our sheet metal shop, where we use techniques like welding, laser cutting, and forming to create large assemblies. Down here, we do much more than production. We also do research and engineering. One of the great examples of this is the human surrogate torso. This torso manages to combine multiple techniques down here. We have additive manufacturing, we have composites, we have instrumentation, we have polymers, all in order to evaluate the impact of ballistics through armor and on our personnel in the field. One of the critical technologies behind this is 3D printing. Let's come take a look. Hey, Bramy, why don't you tell us a little bit about 3D printing?
This is our SLS machine. It produces glass-filled nylon parts like this, where you can see the layer lines. The resolution is very high, so the parts come out really smooth. The glass-filled nylon is one of the strongest polymer materials that we have here at the lab. We also do metal and amongst other types of materials in other machines. And we collaborate with people across the lab for research and design and fabrication.
Thanks, Bramy. Let's go take a look at composites. Hey, Ron, why don't you tell us a little bit about engineered materials?
Certainly. So down here in the composites lab, we primarily deal with PMCs, or polymer matrix composites. We use different resins such as epoxies, cyanide esters. We use reinforcements like carbon fibers, glass fibers, Kevlar fibers. So this, for example, is a fiberglass impregnated fabric, and it is impregnated with an epoxy resin. And we can build different structures. This is super drapable. We can achieve complex geometries. This is a carbon fiber part that we built for a telescope. Another application is a carbon fiber bracket that was used on a spacecraft. It, however, does not use a unidirectional product, but a woven product. And with these products, you can achieve geometry something like this.
We're not just limited to polymers and composites, though. We can also 3D print metal. This machine is another one of the ways that APL is investing in the future of manufacturing. This metal additive manufacturing machine gives us the capabilities to do materials and geometries that were impossible to do previously. Things like lattices, complex lightweight structures, or topology optimized parts, which take their inspiration from nature to create strong, stiff parts. Or hybrid approaches that take the best of machining and combine them with this new technology to do things we couldn't do before.
So that was a whirlwind tour through our shops. There's a lot more than you saw, but that gives you sort of the flavor of what we can do. What I'm going to do now is show you a video clip that basically follows a part through the life cycle, from design through planning, through manufacturing, through testing, integration, all onto a spacecraft. The part that we're going to look at is a bracket for a hinge assembly. All right, why isn't it cooperating? Having fun trying to get the thing to change screens on me. I did. Try again. There we go. Okay. So Parker Solar Probe is a satellite that is currently orbiting the sun. Parker was the gentleman who originally discovered the solar wind. And so we named this project after him. The idea of Parker Solar Probe is a satellite that follows an orbit much like a comet. It starts out far from the sun, loops in close to the surface, and then back out. This is to allow us to collect data down inside the edges of the solar atmosphere. We're within 9 solar radii of the surface of the sun, or the center of the sun. So it's well inside the Mercury orbit. The front end of this satellite has a heat shield on it. The front face of that heat shield will hit 2200 degrees Fahrenheit when it's closest to the sun. The rest of the satellite hides in the shadow behind it. It will actually, the body of the satellite will actually be at room temperature. So let's go ahead and play this, and then as you go along, if you have questions, save them, and we'll try and address them later. So there was a lot happening in there, but basically what you saw is we started with the design. They planned the project. They picked certified space qualified material. So you want to make sure the part's not going to break. They machined it, then they inspected it. The inspection system can measure down to 10 millionths of an inch, so we get a very accurate image of how well we've manufactured the part compared to the original drawing. Then you saw the man putting in helicoils, which are inserts that allow the screws to go in and not gall. And then he laser marked it. Then it went into storage until it was needed. At the end there, you saw out on a table, they had a low friction surface table that allowed them to do the deployment testing here on Earth, because we had to simulate how it would behave out in zero-G conditions. And it worked. The satellite is now actually coming up on its second year in operation. It's gone close to the sun 3 times, and it's getting ready for its 4th approach. It's collecting some really unique data. All right, let's see if we can flip to the next one. So I've been showing you so far what we do in mechanical fabrication. We're now going to take a walk over to another building on campus and show you what our electronics fabrication capabilities are.
Hey, Scott.
Hey, Matt, how you doing?
All right, how are you?
Good.
I've come up with this great idea. I drew the circuit for a cloaking device. I was hoping you could make me a quick prototype.
Well, let me think about this.
Scott,
Paul.
first cloaking device completed.
Ah, thank you.
Welcome.
Here you go, Matt.
Wow, this is great. Wow, this is great.
Hi, I'm Alan Keeney, Group Supervisor of the Advanced Electrical Fabrication Group. The Johns Hopkins Applied Physics Laboratory has a unique capability to fabricate complicated electrical hardware on the campus. We have a full, vertically integrated fabrication facility that builds anything from difficult prototype boards, such as those on the prosthetic limb, to complex, high-reliability electronics for spacecraft, such as Messenger, Stereo, New Horizons, and the Van Allen probes. Last year, our group built thousands of electronics boards, cables, and assemblies for every business area of the laboratory. The skills and experience of our staff allow for tailoring to your specific needs. To learn more about the Advanced Electrical Fabrication Group, visit our website.
I don't know if you caught it. It looks like the edge of the screen's cutting the videos a little bit, but they did have a disclaimer. We do not actually have any cloaking devices yet. All right. Absolutely. Go ahead.
Right. So just a moment. Let me open up the chat. So what is the coolest thing you designed and what purpose did it serve?
I do not actually myself do much design work. I do a little bit. I'm more involved from the point where someone has a design idea and I help them pick the right materials. So I'll flip the question a little bit and say, what's the coolest thing I've worked on? I actually have a separate video for that. We'd have to go to the end of the viewgrass to see it. But we had a project some years ago called Revolutionizing Prosthetics. And you saw a real brief glimpse of the product in that last video clip where they called it the modular prosthetic arm. You saw the hand opening and closing. Basically, the project was to develop, it was funded by DARPA, to develop a fully functional limb that had full 23 degrees of freedom that a person could put on and be able to reproduce most of their normal human activities. If you'll be patient, once we get through the other video clips, I'll show a clip of someone working with the modular limbs and actually operating them by thought. That has to be one of the coolest projects. The other thing that I find really cool is the fact that over the years, at least some of the space projects, I have touched and helped fabricate parts that are A, orbiting the sun, B, now all the way out in the Kuiper belt beyond Pluto, and C, orbiting inside the Van Allen radiation belt and going through various other exploratory missions. So it's just fascinating, all the different types of projects that flow through here. Next question.
Yes, one of our audience members has heard that APL has 3D printed a heart, and what materials were used to make that?
3D printed a heart?
Yeah.
Okay, I know there's some work going on in bioprinting, but I'm going to have to plead ignorance. I do not know. Sorry.
That's fine. Can technology like 3D printing help in tissue engineering?
There is work in that area. What I know are things mainly that I have read online and some articles I've seen. The issue when you start building up tissue layers is how to keep them fed and alive. And I know there's a lot of work going on in how to do that. I can't speak to the exact state of the art, but I know people are working in that area. And of course, the goal eventually would be to do something like harvest cells, have harvested cells from a person ahead of time that knows they're going to need a transplant and effectively grow them a new organ. I know that they have effectively printed material and done a replacement bladder for somebody, or at least in an animal model. I don't know if they've done it in a person. But whether they've been able to fully reproduce more than cross-sectional parts of other organs, I don't know.
Okay. What are some special materials you need for the solar probe, and why? And what? And why? And what are some like space qualified materials?
The term space qualified is pretty wide open. Space as an environment is fairly challenging. Once you get outside the Earth's atmosphere, you have energetic particles, you have things like atomic oxygen, where oxygen molecules have broken up and are wandering around individually, which means they're very active and want to oxidize things. You have solar radiation, intense UV. You've got the deep cold of space, and you can also have intense heat depending on where you are and what you're facing. And one of the challenges is you can go in and out of the shadow, back and forth, and so you're doing vast temperature cycling, so huge amounts of thermal transit that has an effect on materials' coefficient of thermal expansion. So we also look at what happens when you put a material in space and whether or not it outgasses something. So if you take a piece of material like the bathtub caulking you put on your bathtub, you smell a particular odor when you put that stuff down. It's outgassing. Well, a lot of polymers outgas, not necessarily to the level of anything you would smell, but it would have an effect in space where the molecules come off and then collect on the nearest cold surface. And if that cold surface happens to be your solar panel and you start obstructing it, then you can no longer get the electricity you need. Or if it was a lens, you might start fogging up the image. So there's a whole range of things you have to look at, and we understand most of them. We tend to run tests, lots of them. We go back to materials that we have used before. So you want things that have low outgassing, things that are radiation resistant, and so on. In terms of things on Parker Solar Probe, what was really unique about that is the high temperatures. So the front end thermal shield on that, the bulk of it is made up of 2 layers of what's known as carbon-carbon, which is a carbon fiber and a carbon matrix. The material is stronger at 5,000 degrees Fahrenheit than it is at room temperature. In between the two layers of carbon-carbon, we sandwich 4 inches of carbon foam. It's an open cell foam, but the rest of it's all made out of carbon. Those are bonded together with a carbon adhesive. And then the front face of the outer surface has a special ceramic coating on it. It's proprietary. And that's what basically fends off the solar energy. The solar panels on that spacecraft, instead of being a lightweight honeycomb structure, are solid titanium with channels built into them with liquid cooling. It's actually water cooled, just like a radiator in your car. And they will stick the solar panels out into the sun briefly, collect as much energy as they need, and then retract them back into the shadows before they melt. It's like drinking from a fire hose. Next question.
That's really cool. Yeah, so how do you recreate neuronal connectivity for a regenerated organ? I don't know if I said that right.
I know what you mean, and I have absolutely no clue. There are people here in biomechanics and biosciences who would be, experts in that area. Not my area. Sorry.
Okay. Yeah, that's pretty much the last question as of now.
That's fine. Yeah. Let's go ahead and see if we can go to the next video clip then. So what I'm going to show you now, this project, do we know why that video keeps going out and cutting the corners off? I don't know how to stop it. Oh, well. So Krakens. Krakens is a quadcopter. What's unique about it is that it starts by living underwater and then it swims to the surface and then flies. So I'll play this and then I can tell you more about how we made it. Oops. That did not look like it worked correctly. Let's see if we can go back and try again. Hope this works. There we go.
APL researchers have designed an unmanned aerial vehicle, or UAV, that can stay on station beneath the water, then launch into the air to perform a variety of missions. Krakens, the corrosion-resistant aerial covert unmanned nautical system.
APL engineers have long worked on both Navy submarine systems and autonomous unmanned vehicles. In response to sponsor challenges, we were inspired to develop a vehicle that would operate both underwater and in the air. The result is a submersible UAV that can be launched from an unmanned underwater vehicle.
Krakens enables new capabilities not possible with typical UAV or UUV platforms. Its ability to operate in the harsh littoral environment and its payload flexibility enables a wide array of potential missions. Krakens can remain at and launch from a depth of several hundred feet without needing structural metal parts or machine surfaces. To make that possible, the team needed to overcome two big challenges. First, the APL team leveraged advances in additive manufacturing and novel fabrication techniques, creating a lightweight, submersible composite airframe and pressure vessel at low cost. The second significant challenge was to ensure Krakens could operate in a corrosive saltwater environment. So the team designed the UAV to keep as many components as dry as possible. For some parts that couldn't be enclosed, like the motors, APL applied commercially available protective coatings, testing their performance by submerging the coated motors in salt water. After 2 months, the motors showed no sign of corrosion and continued to operate while submerged. The resulting prototypes met or exceeded the team's expectations.
Kraken successfully demonstrated a new way of thinking about the use and fabrication of unmanned systems. It now gives sponsors and researchers access to possibilities that were previously off the table, and the low cost makes it expendable, allowing for the use of large numbers of vehicles for high-risk scenarios.
Krakens has drawn accolades from both inside and outside APL. In 2015, Krakens took the stage as an example of the best innovative UAV thinking during a recent speech by Secretary of the Navy, Ray Mabus. At APL, our culture of innovative ideas and mission-ready solutions persists to deliver success for our sponsors and the nation. With Krakens, APL continues our commitment to creating game-changing solutions for the 21st century.
So, of course, the name is a takeoff on the Kraken, spelled a little differently, but the fabrication of the structure depends on two primary technologies in our area. One is 3D printing and the other is composites. The white structure you see is actually 3D printed nylon with glass reinforcement. So the main pressure body was printed that way. The legs on it, however, were fabricated by printing a different 3D printed material that is actually a support material that can be dissolved away in a hot bath. So we printed the shapes, wrapped composite materials over that and cured them in a vacuum bag. And once they were cured, we etched out the tool from the inside, left us with hollow, lightweight structures. We incorporated features to allow it to mount the motors to it and so on. So it was a combination of different technologies, and it's worked out really well. All right, let's see what the next one is. All right, so now I'm going to give you a video tour of the ISC, the Intelligent Systems Center. For those of you who are into robots, this is our Robot Central. If you watch closely, you'll also see the modular prosthetic limb as they go whizzing through this place.
Welcome to the Intelligent Systems Center, where we're inventing the future of intelligent systems through cross-disciplinary research in machine learning, robotics, autonomous systems, and applied neuroscience. The ISC is a center of excellence for APL and for the nation.
that was a really quick run through of the ISC. There's a lot there. We obviously have a fair interest in robotics from all different angles, AI and so on. A lot of the things you saw, we fabricated many parts of here in our facilities. All right, so let's see, where are we? So I'm going to leave you these two links. Now, we still got a couple other things to look at if you want to. But that's the YouTube address. The videos, as I noted, were getting slightly cut off on the edges. If you go to the YouTube site and do some searching, you can find all the videos you saw today, plus a lot of others. And then APL's primary web address is there. The APL web address will lead you into our front page. And from there, you can find a link for internships and for jobs. We do offer interns for high school students, junior and senior level, I believe, and also for college students. And yes, some of the interns actually end up working here. One of the gentlemen in our additive manufacturing area started out in high school, kept coming back every year through college, and now he works in our facility. So it can be a link into the place. If nothing else, it gives you a wonderful exposure to a whole variety of different technologies. Any other questions popped up?
Yes, we've had a lot of questions.
Okay.
Yeah. So yeah, let's start with the first one. How do you make a 3D printer?
Printer or printed parts? We don't make our own printers. The ones we're using are all commercial. A number of them are industrial scale machines, companies that specialize. Each printer is unique to the process that it does. So some of these, let me, I'm going to stop sharing for the moment so you can see my face instead of listening to me voiceless over the image of the blank screen there. In the area of polymer additive fabrication, there are a number of primary types. One basically takes a strand of material, feeds it through a nozzle, melts it, and draws with it. It's like a high-tech hot melt glue gun. We have a couple of systems like that. Our biggest one is like that. It can build 2 by 2 by 3 feet at a time. It doesn't produce as fine a resolution, but it does produce very durable thermoplastic parts. And it also uses the material that we talked about that we dissolve to make the throwaway tooling or dissolvable tooling for the composites. The next system we have is one that takes inkjet print heads, 196 of them. As it scans over the table, it squirts material out of various inkjet heads as necessary to put down little droplets, which are then UV cured, a layer at a time. It builds about 30 micron layers and just keeps building as it goes. That works in acrylic resins. It produces really fine detail, really fine finished parts. They're beautiful models. They're just not very good mechanically. So it's very useful for doing a display model or something that we want to turn around and make a rubber mold off of and cast into another polymer that has better properties or more specific properties that we're after. And the third type we have, you saw in the video, in the initial video, where they talked about solid laser sintering. That takes a powdered thermoplastic, in this case nylon, and spreads a thin layer of it on a table, and then a laser comes back and fuses just the part you want to make solid parts out of. It then lowers the table a notch, fresh layer of powder, repeat, and you fuse layers through to the previous ones as you build. When you're all done, you basically, once it cools down, you do archaeology and dig through all the powder and find your parts. And we can build in a 1 by 1 by 2 foot volume like that. That's how that pressure body for Krakens is manufactured, and lots of other parts. The properties are pretty much the same that you can get out of an injection molded part. So it's very durable, very, very useful. You're sort of limited to one color, but you can dye it or paint it. In the metal area, it's basically done with powders the same way as solid laser sintering, but it's done with higher energy lasers in a special atmosphere so it doesn't burn up. And so it spreads a layer of powder over a metal base, fuses initially to that base, and then starts building. Now, you can't just have them floating loose in the powder. You have to have a connective network of supports because the high heat involved in doing the metal would cause things to warp if they weren't supported or held in place, and they get in the wrong place and then get hit by the spreader bar, and you'd lose your part. So we can build in a whole range of different metals. We can also blend metals and ceramics together. We're doing some very innovative stuff in that area. So those are the variations. But in terms of the machines, there are plans out on the internet for building your own. I've never tried it, but I'm sure it would be an interesting project. And those would be ones probably that melt the polymer through the nozzle and draw with it.
Yeah, you actually answered the second part of the question, like what types are there and like how do they work? So that's awesome. Yeah, so this is also another one of those two-part questions. In what way do you collaborate with bioengineering labs and the renewable energy field?
Okay, the bioengineering people, for the most part, would come to us if they needed instrumentation, some sort of new housing built to hold instruments, some test fixture that they're going to use. We don't actually do the bio part over here.
Right.
We're plain and hard materials. We're basically here to help solve people's problems. And if we can't find a way to build what they need in-house, we'll help them find somebody outside that can do it. We also obviously could build some of the electronics that you saw. And then if it's molding something, creating a structure that they're maybe going to grow their materials on, things like that, we can work in that area. And the second part?
Yeah, the renewable energy field.
Renewable energy, I'm sorry. Lately, I don't know that we've had any projects in that area immediately. Some years ago, we did some stuff on a natural gas powered vehicle. We worked with an outside company that filament wound a composite tank, and then we built special energy absorbing buffers that went around it so that if the car were in an accident, it wouldn't burst open the tank and cause a problem. We have also, before I came here, I think, so it's been a while, they were working on some devices that you put out in the ocean waves to harvest energy. But I don't know, currently, there may well be people doing stuff in that area. I'm just not aware of it.
Right. And why did you choose the job you have now? And like,
all right. So when I went to college, I was convinced I was going to go into nuclear engineering. I got to RPI and found out that meant simultaneously majoring in math and physics. I could do one or the other, but not both at the same time very well. I was struggling a bit. I had a really good advisor. Sat down with him and talked to him. And he's basically got me to think about what part of nuclear engineering fascinated me the most. And it turns out it was the materials problems. Well, at that point, fortune had shined on me. I was at one of the 4 schools in the nation back then that had an undergraduate materials engineering program. RPI had a program set up by the NASA to support the space program. And so I transferred into materials. Once I was through RPI, I had studied metallurgy and glass and ceramics and polymers, and I had assisted a graduate student in building a composite hip joint replacement, and that's how I got into composites. My first job, which was not here, was working in a corporate research lab, setting up test capabilities, mechanical and thermal testing and electron microscopy and so on, full materials lab, as well as building test apparatuses to support the various researchers. That company, after 3 years, got bought out. I moved to another division of the company and started working in carbon-carbon aircraft brakes, which was a specialized composite area. I worked both on processing and also on materials testing. After about a year, for a variety of reasons, I started looking around for another job. I came out to Maryland again and looked at what was back then Martin Labs, before it became Lockheed Martin. The old Martin Labs over on the other side of Baltimore. They used to build aircraft and spaceships and all kinds of different things. I was involved in building missiles, composite missile structures. And I did that for about a year. And they wanted to move me, and I didn't want to move to where they were wanted to go. I liked the area here, so I started looking around. And a position opened up here at APL to start building composite materials in-house. That was 34 and a half years ago. And I've been here the whole time trying to grow and build that capability, both in composites, polymers, adhesives, you name it. And I've stayed here because there are very few other places where you can do the variety of different things you do in one day. I mean, I'm not saying every day we do a whole range of things, but there's just such a variety of different projects here. It keeps my interest level high. They very much encourage innovation. I don't know if if you go on our website, you'll see that Fast Company just named us the #3 place in the country for innovation. And I'll back that up. I've been fortunate enough over the years to be able to get a number of US patents in different areas. It allows me to be creative. It allows me to do problem solving.
Yeah, that's great. Yeah, so I came up with a couple of questions. One second. Actually, I'll do the audience questions first before I get to mine. I'm sorry.
Okay.
How important is carbon in your work?
Carbon, pretty high. Carbon fibers in composites are one of the primary reinforcement mechanisms that we use. The carbon that we talked about before, we don't actually process the carbon on site here, although I did, as I noted, work for a company that did that previously. It takes some very specialized high temperature equipment that we don't have in-house. But those get used in very high temperature applications like the sun shield for a solar probe. And then just raw carbon itself gets used for things like electrodes or for things like low friction surfaces. You can use a version of a graphite as a lubricant. So we get into all sorts of it.
Cool. What project inspired you the most?
You've seen part of it already. And let me go back to sharing and go to a different screen and show you a video of the modular prosthetic limb. Now, to explain, the MPL was a project that DARPA had to replace human limb that had been injured or lost due to combat. Prior to this, most of the limbs that people would wear had a simple cable mechanism that when you bent a certain way, it would close like this, and that was it. We wanted something that actually gave you full function. And so the idea was to blend robotics with biomechanical engineering to build something that could fit on a person. So let me get back to sharing. Go here. Is that showing correctly?
No, I think you have to go to
You still have to go to the... Okay, that's not showing up on here.
It's at the top. Display.
I know, but it's not coming up. Let me get out of this mode just a moment. Hang on. Okay, start sharing again. I'm still not seeing that link. That's not good.
Not coming up.
I apologize for the delay here. Let's do it this way. See if I can get this to behave instead. You seen an image or not? The PowerPoint program, right?
I think you have to press present. Just press present. It'll, and then just go back a couple.
There we go. Now I need to swap it. Bingo. Finally found our way back. Okay, now. So here is a person actually controlling 2 of the prosthetic limbs with his brain alone. So what you're seeing is a virtual reality environment that he's manipulating first. If you think about that, they're managing basically to read signals from the brain directly and manipulate a robotic arm. Now, as you can see, it still needs refining, but where that is compared to where they started, it's pretty amazing. We had a quadriplegic woman who came through as part of the test program, and she was one of the first people. They actually had to penetrate a probe right into her brain. And she was able to fly an F-35 in a flight simulator through the Grand Canyon just by thinking of it, which pretty much blew my mind. But that project, the limb, first we had to come up with the robotics capability. We had to build something that was compact enough and lightweight enough that it would fit on a human and operate correctly. It's not the $6 million man, because although the limb can exercise a lot of force, it still has to be translated into the human body. And unless you translate directly into the skeleton system by penetration, you've got to figure out how to spread that load out over the human torso. And we've done that successfully. I've actually shaken hands with somebody wearing one of the limbs. It's pretty impressive. It inspired the living daylights out of me.
Wow, that was really cool. It's, yeah.
There are other videos out on their YouTube website too for you to look at.
Yeah, I'll be sure to check it out. If you could, if one of the tech people could put the link to their YouTube channel in the chat, that would be.
Now, the other thing that I know people typically want to know is, what else are we working on right now? So let me show you a couple of programs that are just starting, or at least there's some video clips about them, just to give you an idea of where we're going. So let's go back from this. We'll get to that. Dart. Yes, we are actually trying to defend it. Unlike the movie Armageddon, we're not going to blow it up.
DART is the double asteroid redirection test. The Earth is hit by asteroids and pieces of asteroids all the time. Every year or so, we get hit by things maybe the size of a table. The kind of object that DART is going to visit is an object that's about the size of the Washington Monument. Those kinds of objects hit us every few thousand years, and they would cause severe damage on a regional scale.
We chose to do this demonstration at a binary asteroid. It's called Didymos. This is actually approximately the shape of the main asteroid. It's called Didymos A, and its moon, Didymos B. What DART will do is DART will hit the secondary. When it hits the moon, it will change the orbit period. And when it changes the orbit period, it affects the timing of when the moon moves in front of or behind the primary.
Mostly what we're looking to do is change the speed of the incoming object by maybe a centimeter per second or so. So that's not very fast, but if you do it enough seconds in advance, you can cause it to miss the Earth entirely.
DART is the first mission to fly the next C ion engine. It is the first mission to demonstrate smart navigation, which means we're going to be guiding ourselves into the asteroid autonomously.
At about 4 hours out from impact, SmartNav is kicked in, and what it does is it uses the imagery from the optical payload, basically the camera that's on DART, and from the imagery we are able to discern Didymos A from Didymos B. We have a targeting algorithm that differentiates the two, and we are aiming for Didymos B.
The other part of this is the propulsion system that we're demonstrating. The NextC propulsion system is utilizing a new generation of gridded ion propulsion technology, and it's what we're using to allow us to get to the asteroid, but also allow us a flyby of an object prior to our actual encounter.
For this vehicle to be able to supply the power for the electric propulsion engine, we needed higher power output. ROSA allows us to be able to have a very compact and light mass for launch and then deploy these really large arrays once we're out there in space.
Our planetary launch window opens on June 15, 2021, and will impact the asteroid in 2022. We're very excited to be NASA's first planetary defense mission.
So I thought that's really cool. I think we're technically about out of time, right?
Yeah, we're out of time. So
all right. So I would encourage people to go visit our website, visit the YouTube channel, and when you're there, search for the word dragonfly. And that's the other video I was going to show you. That's the quadcopter that'll fly in the atmosphere of Titan. Thank you for your attention today.
Yeah, and thank you, Mr. Biermann, so much for taking the time to give us a virtual tour of JHU, APL, talk about some of your projects. Like, I'm speechless about how cool they are. So, and ConnectCon would not have been possible without you or any of our speakers. Also, thank you to our alumni attending here today, Ishan Oberoi, Sarthak Bhatnagar, and Angeline Zhang for their help. Lastly, thank you to our audience for being attentive and kind. We hope to see you all tomorrow for our next two sessions. In the morning, we have Dr. Alicia Weinberger, who will be talking about potentially habitable planets and how to find them. And Dr. Meenakshi Patel will be talking about emerging technologies and making the leap effective in the afternoon. We'll see you all tomorrow. If you have any more questions regarding the presentation, please be sure to email them to us and we'll forward them to Mr. Biermann. Please make sure to like and subscribe to our YouTube channel, Wizards.exe number 9794. Follow us on Twitter, Instagram, and Facebook, and check out our website if you want to find out about more STEM opportunities like this. Thank you once again to Mr. Paul Biermann from all of us here today.
You're welcome.